I do want to talk a little about the comparison test for improper intervals. So let's look at a couple of examples. Let's say I wanted to determine, so in these problems, we're not being asked to tell what something converges to. If it converges, we're just being asked to say, does the thing converge or diverge? So let's look at this first example. The integral from 1 to infinity of dx over x plus e to the x. So to use the comparison test, you have to have a function or integrand that's always positive, and you have to be able to compare it to something that we know has an integral that's either convergent or divergent. So here's what I'm seeing. I'm seeing that 1 over x plus e to the x is less than 1 over e to the x. Right? If your denominator is larger, your fraction is smaller. And this denominator is certainly larger than that denominator everywhere from 1 to infinity. And then I can say, well, I know, and you guys know, that. So that's an excellent question, Morgan. How do you know what to compare it to? It takes practice is really the right answer. So the problem is comparing it to 1 over x. In fact, let's talk about this, and then we'll talk about why 1 over x doesn't work. So we have to kind of have some idea if we think it's something that's convergent or not. I think this is convergent because I'm pretty sure that 1 over e to the x is convergent. Let's take a look at it. The integral from 1 to infinity of 1 over e to the x, or e to the negative x, is the limit as t goes to infinity of the integral from 1 to t of e to the negative x dx, which is equal to the limit as t goes to infinity. Integral of e to the negative x is e to the negative x divided by negative 1, or negative e to the negative x from 1 to t. Plug in the t. I'm going to write this as the limit as t goes to infinity of, negative 1 over e to the positive t minus negative 1 over e to the 1. So the limit of this, well, as t goes to infinity, e to the t goes to 0. So this part, e to the t goes to infinity, so this fraction goes to 0. And minus minus is plus 1 over e. So here's what we can say. This integral, that integral converges to 1 over e. This integral, because this function is less than this function, I'll draw a picture in a second, this integral also converges by the comparison test. This converges, I'm going to write that down. So here's the idea in this example. So I'm going to draw this function not very well. I know if I plug in 1, I get 1 over 1 plus e, which is super small. Let's say it's like there. And this function, 1 over x plus e to the x, does get smaller and smaller and smaller as x is larger and larger. So this function, I don't know what it is exactly, but it looks kind of like this. So here is, in green, f of x equal to 1 over x plus e to the x. And now here's what I'm going to say. In red, here's the function 1 over e to the x. Also getting smaller and smaller and smaller, but is definitely bigger than this function. Okay, here's the sum up. We just showed that this integral of e to the negative x from 1 to infinity is convergent. In other words, we just showed that the area under this curve we showed that all of that area out to infinity is a finite amount. It's actually 1 over e. Well, here's what we get to say then. The area under the green curve looks like that. I'm going to ask you guys 2 questions, which are just yes or no questions. You can even click the little buttons. Question 1. Is the area under the green curve positive? Yes or no? Yes, exactly. Okay, question 2. Is the area under the green curve less than the area under the red curve? You guys are like, yes, still. Right. So since the area is positive and the area is less than a finite number, it is also a positive finite number. So it converges. That's it. That's the comparison test, if you're trying to show something converges. So to answer the original question about, or to the original suggestion about comparing to 1 over x, we can't compare to 1 over x here. Well, we can, and we'll see it won't work, because if you think the thing is convergent, comparing to something divergent won't actually show you anything helpful. So here's what I mean. It is also true that 1 over x plus e to the x is less than 1 over x. For sure true, for the same reasons. This denominator is larger, this fraction, so that means this fraction is smaller. All right? So then, at least on the interval from, and now we know this interval from 1 over x, from 1 to infinity. We've done this one a few times. If this diverges, we know it diverges by the p-test. You can do the work, right? It's the limit as t goes to infinity. The interval of 1 over x is the natural log of x. Evaluate from 1 to t. You plug in the t, you get infinity. Right, and this goes to infinity, so you get divergence. All right, so here's what we've said, which isn't very helpful. Here's 1 over x. Starting at 1. And now here's 1 over x plus e to the x, which is a little bit smaller. Okay, so I'm gonna essentially state the same questions. Yeah, this area in red, or sorry. So the area in red is still less than the area in green. But here the area in green is infinite. And so showing that this integral has less area than this integral doesn't really tell us anything. Because if I have less area than an infinite area, I could still have an infinite amount of area. Or I could have a finite amount of area. So if you think something is convergent, you have to compare it to something that is convergent. If you think something's divergent, you have to compare it to something you think is divergent. So the real kind of bigger piece of this is that we have to have an idea about what happens before we can really do anything. Okay, let's look at some more examples. Let me ask you guys, did you talk about the limit comparison test for integrals or just the comparison test? Anyone talk about the limit comparison test? Both. Okay, great. So, well, let's look at some more examples and then we'll talk about limit comparison. So look at this example, the integral from e to infinity of 1 over the natural log of x. Now I'll tell you, this one usually in the past is really kind of, is this the one that's really hard? Maybe not. This one I've maybe found stumping before. I would say, right, you can just, not this one, but other problems, you're welcome to just actually integrate. I think if someone asks you this one, the integral from e to infinity of 1 over x, natural log of x. This one you just want to use the integral, right? You want to do a u substitution. This becomes the integral of 1 over u, which ends up being the natural log of u, which is the natural log of x. So you can see that, okay, you're going to get the natural log of something that's going to infinity. So this one's going to diverge. So a problem like this, if you can actually integrate it, it's usually the way you want to go. This one, I don't think we can. So instead, we start thinking about, well, shoot. Well, I think we can actually compare this to 1 over x. I I'm pretty sure that the natural log of x is less than x. If you're not sure, graph the thing. Here's y equals x. Here's y equal to the natural log of x. Oh yeah, it seems pretty clear that y equals x is always bigger than y equals natural log of x. So now, flip them. When you flip things, you change the order of the inequality, or the direction of the inequality. In case that seems weird to you, just think about the fact that 2 is definitely smaller than 3, but 1/2 is definitely bigger than 1/3. That might make it a little bit more obvious that, oh yeah, we have to change that direction. So in this problem, we can see that, oh look, this function is bigger than that function. They're both always positive. So we can say that this integral diverges by comparison with, I don't know, I would write the other integral. Right, and we know this is divergent by because it's by the p-test. The integral of 1 over x to the 1 definitely diverges. But yeah, knowing what to compare something to really is kind of something you have to practice. Let's look at another example. Okay, this example is going to seem not terrible, but it's a little. So let's say I want to talk about the integral from 3 to infinity of 1 over x minus 1. All right, I'm pretty sure this is just like 1 over x. And we know that 1 over x is divergent. Or I should say, we know the integral of 1 over x is divergent. However, you can't just directly compare that to 1 over x. Or can I? No, I picked the wrong way. Sorry. Let me fix the problem slightly. There. Now it's actually what I want. So I'm still pretty sure. Right, it shouldn't really matter if I add or subtract 1 in the denominator. I'm really just kind of moving over the integral a little bit. It shouldn't really affect whether it's convergent or divergent. But here's the issue we encounter when we look at this. If I wanted, well, I guess I could integrate it. I'm just trying to be, sorry. You could totally integrate this one and see it's divergent. Okay. But if you want to use the comparison test, you can't say what you want to say. Because 1 over x plus 1 isn't bigger than 1 over x. 1 over x plus 1 is actually smaller than 1 over x. You could do some tricky manipulating if you wanted to try and make this thing something that's bigger than 1 over x, but here's the other thing you can do. This is the limit comparison test. So 1, we know that the integral from 3 to infinity of 1 over x is divergent. 2, we can look at the limit of the unknown integrand divided by the known integrand. The limit as x goes to infinity of 1 over x plus 1 over 1 over x. We're going to simplify. That's the limit as x goes to infinity of 1 over x plus 1 times x over 1, or just x over x plus 1. And what's this limit equal to? Well, it's 1, right? Quotient of the leading coefficients. And importantly, this is not 0, and it's not infinity. So here's what we get to say. This is the comparison, the limit comparison test for integrals. If you take the limit of an integrand over a known integrand, if that limit is equal to a non-zero finite number, like 1 or 3 or pi or 7, then this integral has the same behavior as that integral. So if we know this one diverges, we know this one diverges. You could also have integrated this one, right? We can integrate that and get the natural log of x plus 1 and then see that it goes to infinity as x or as t goes to infinity. But that's the idea of the limit comparison test. Let me show you a better example, or an example where you actually really need to use it. How about this? How about does this integral from 1 to infinity x squared over x cubed plus x plus 5. Does this converge or diverge? So when you got rational functions like this, the idea is really just to compare the highest powers. So I see an x squared over x cubed. So I see that this x squared over x cubed plus x plus 5 looks a lot like, or acts a lot like x squared over x cubed, which is 1 over x. So I'm pretty sure just by doing that amount of work right there, I'm pretty sure this thing's going to diverge because it's an integral of something that's essentially 1 over x. But to show it, we have to do this. The limit as x goes to infinity of the unknown thing that you're trying to say whether or not it diverges or converges. Divided by the known thing. So we are limit comparing this with 1 over x. So limit comparing with, which we know is divergent. This limit is going to equal limit as x goes to infinity, x cubed over x cubed plus x plus 5, which is certainly 1. And as long as this limit is not 0 and not infinity, this integral and this integral have the same behavior. I should say this integral from 1 to infinity, and this have the same behavior. So this integral converges, diverges. Sorry, this integral diverges. This also diverges. But I needed to use this here, right? Because this, I couldn't just say was bigger than 1 over x, right? This is actually smaller than 1 over x, but it's smaller in a way that it's still divergent. Okay, let's look at a couple more examples. Sure, let's do one. What if instead, that's an interesting idea. Sure. Yeah. What if I had the integral from 2 to infinity of x over the square root of x to the 6 minus 1? Certainly possible that we could actually integrate this. You might be able to do some crazy u substitution. That's not the point though, right? The point is just to compare. To me, this looks like x over the square root of x to the 6th. Right? Again, I'm kind of just paying attention to the highest powers. This looks like x over the square root of x to the 6th, which is x over x cubed, which is 1 over x squared. I'm pretty sure, since this is essentially like 1 over x squared, that it's going to be convergent because the integral of 1 over x squared from 2 to infinity converges. So I'm comparing with the integral from 2 to infinity of 1 over x squared, which is definitely convergent. Now, I couldn't do a direct comparison here because this thing here, which is bigger, this thing or this thing? Well, this thing has a slightly smaller denominator, so this one is the slightly larger thing. So unfortunately, x over the square root of x to the 6 minus 1 is bigger than 1 over x squared. And being bigger than something that's convergent doesn't tell me, right? If I have more area than something with finite area, I could have finite area. I could have infinite area. So we don't know, right? You can only use the comparison test in the right way, right? You can say you're less than something that has finite area. Oh, we're also finite. We also converge. Or you can say you're bigger than something with infinite area. Oh, I also have infinite area. I also if you're smaller than something with infinite area, or if you're bigger than something with finite area, we don't know. So instead, we're going to say, well, I'm going to use the limit comparison test. I'm going to take the limit as x goes to infinity of the unknown thing divided by the known thing. So this one's going to be a little bit funkier. This one's going to be the limit as x goes to infinity. Let's see, if I flip and multiply, I'm going to get x cubed over the square root of x to the 6 minus 1. How do I deal with that? Well, it's kind of like a rational function where the degree on top and the degree on the bottom are the same, except it's not actually. So we can't just say it's 1 without doing a tiny bit more work. What I'm going to do is I'm going to factor out x to the 6th from inside the square root. So this is equal to the limit as x goes to infinity of x cubed over the square root of x to the 6th times 1 minus 1 over x to the 6th. And then the square root of x to the 6th is x to the 3rd. Technically, it's the absolute value of x to the 3rd. But since x is positive, the absolute value of x to the 3rd is x to the 3rd. So this is x to the 3rd over x to the 3rd times the square root of 1 minus 1 over x to the 6th. These cancel. You're left with a 1 over 1 minus 0, which is just 1. So once again, since this limit is not 0 and not infinity, this integral and this integral do the same thing. So this integral converges. Yeah. That's most of the idea behind the comparison and the limit comparison test, is you have to have some sort of intuition about whether a thing might be convergent or divergent. And for a lot of them where you just have like powers of x, it's usually pretty easy just to be like, well, what's the highest power on top and bottom? For example, I'm not going to do this one. 1 over the square root of x squared plus 1. But I'm 100% confident this diverges because 1 over the square root of x squared plus 1 is acting like 1 over the square root of x squared, which is 1 over x. This is definitely going to diverge. The way you would show it is by showing that the limit is x goes to infinity of the unknown thing over the known thing. That limit's going to end up being not 0 and not infinity. It's going to be 1. A lot of them end up being 1. Not always, though, so don't like get used to it always being 1, because it's not always going to be 1. Let me see. Something, sorry, excuse me. Something I wanted to say about this. Oh, technically, if you're looking for divergence, it's okay to get infinity. If you're looking for convergence, it's okay to get 0. But you probably won't. Let me look at one more. So on the other hand, let's look at this one. The integral from 1 to infinity of 1 over x square root of x squared plus 1 dx. This one, on the other hand, I'm definitely convinced that this one's going to converge because it's acting like 1 over x times the square root of x squared, which is 1 over x times x. So this is acting like 1 over x times x, which is 1 over x squared. And we know that the integral of 1 over x squared is convergent. So this is also going to be convergent. And again, this one, you could actually use the direct comparison test because it is in fact true that 1 over x times the square root of x squared plus 1 is just less than 1 over x squared, right? The square root of x squared plus 1 is definitely bigger than x. So 1 over the square root of x squared plus 1 is smaller than 1 over x. And then multiply by x here and by x here. And oh yeah, smaller. You could also use limit comparison. It would be fine. You could also make your life terrible and do both of these with a trig substitution. Definitely wouldn't do this one with a trig sub because, well, one, you don't have to, right? Diverges, it diverges. On the other hand, if someone asked you what this converge to, then you'd actually have to do the integral. So I want to make it super duper clear, because I didn't before. Using the comparison test, you never actually know what anything converges to if it converges. You only know that it converges. So I know here by the comparison test that this integral is convergent. But then if someone was unkind and said, well, James, what does that converge to? We'd have to do the work. Is it terrible? It's probably terrible. Let's do it anyway. It's good to remind ourselves of trig subs every once in a while. And then we'll talk about some trapezoid and Simpsons. Okay, so let's see. We were doing this. Integral from 1 to infinity of 1 over x squared of 1 plus x squared. X squared plus 1. Either way, it doesn't matter. I'll try 1 plus x squared. Okay. I really don't like doing a definite integral where I have a lot of other things to handle. So I'm just going to do the indefinite integral first. And then at the end, I'll worry about doing the limit stuff and all that jazz. So let's do, let's see, x equals tangent theta. Dx is secant squared theta d theta. This is going to be the integral of 1 over tangent theta times, okay, why do you pick x equal to tangent? Because 1 plus tangent squared is equal to what? Anybody? It's my favorite trig identity. It should be yours too. Okay, fine. You guys are going to be quiet. All right. Yeah, thanks, Mariah. Secant squared theta, exactly. I tan and get sexy. Unforgettable. So 1 plus tangent squared is secant squared. The square root of secant squared is just secant. And dx is secant squared theta d theta. Cancel secant there and secant there. And you're left with the integral of secant theta over tangent theta. And there's probably a way we can rewrite this to make it easier. Let's see. Secant is 1 over cosine. Tangent is sine over cosine. Oh yeah, this is going to be great. This is going to be the integral, let's see, 1 over cosine, sine over cosine. The cosines cancel, you get 1 over sine, which is cosecant. Just to make sure everyone's on board with that, right? I had 1 over cosine, I had sine over cosine. I said, oh yeah, if you flip and multiply, the cosines cancel and you get 1 over sine, which is cosecant. And then the integral of cosecant is something we are just kind of expected to memorize. There's 2 versions of it. I prefer the, what version do I don't know. I prefer, I think, the negative natural log of the absolute value of cosecant theta plus cotangent theta. There is another way of writing it, though. It is also equally correct to write that it's positive natural log of cosecant theta minus cotangent theta. It's interesting. It's interesting that if you bring this -1 up as the power here, it is actually true that the reciprocal of cosecant plus cotangent, so it's actually true that 1 over cosecant theta plus cotangent theta is equal to cosecant theta minus cotangent theta. You don't need to show that, but it is actually true that, right, if you bring this -1 up here, this to the -1 power is equal to just that. Who knew? I mean, you guys probably knew, right? You can see it. If you multiply this over here, you get cosecant squared minus cotangent squared, which is equal to 1. That's another trig identity. Trig identities abound. So anyway, doesn't matter which one we pick. But now we do need the triangle. We have tangent theta equal to x over 1. Excuse me. So tangent is opposite over adjacent. The third side is the square root that started the whole thing. So using this one here, we get that this integral is equal to negative natural log of the absolute value of cosecant of theta, which is the reciprocal of sine, which is not opposite or hypotenuse, but hypotenuse over opposite. So it's negative natural log of the square root of 1 plus x squared over x plus cotangent theta, which is not x over 1, sorry, not x over 1 over x. Okay, so that's the integral of that. Now here's what I'm going to do. To figure out if it converts, to figure out what it converges to, I'm going to write the integral from 1 to infinity of 1 over x square root of 1 plus x squared dx equal to the limit is b goes to infinity of the integral from 1 to b of 1 over x squared root of x squared, or 1 plus x squared. We did the integral. We got this mess, which I guess we could write as one fraction. I could write this divided by x, although it might not be in our interest too, but we will anyway. This is equal to the limit as b goes to infinity of negative natural log of the absolute value of square root 1 plus x squared minus 1 all over x from 1 to b. So we plug in the b, limit as b goes to infinity of negative natural log of square root of 1 plus b squared minus 1 all over b minus negative natural log of the absolute value of the square root of 1 plus 1 minus 1 over 1. That looks like a big 0. Right? Oh. That's terrible, James. I was seeing a 2 minus a 1, which I was thinking was 1 over 1, but that's not 2, that's the square root of 2. That is not a big 0. I'm a big 0. No, I'm just kidding. Not a big 0. Not 0. Okay. So now we have to evaluate this limit. Now here's the good news. We already know this thing converges, right? We did the comparison test. We saw convergence. So we have to just convince ourselves that this limit is equal to whatever it's equal to. And here's what I would probably do. I would probably... How would I deal with this? Good question. How would I deal with it? I feel like it's a L'Hopital's rule kind of thing. Maybe. I feel like L'Hopital's rule might be kind of overboard. Yeah, I don't want to use L'Hopital's rule. I think, okay, here's what we have to do. Anyway, in here I'm going to factor out the b squared. So right, this is the limit. B goes to infinity of negative natural log of the absolute value of the square root of b squared times 1 over b squared plus 1 minus 1 over b. Seems like it's going to be funky. Plus the natural log of the square root of 2 minus 1. And then here, I'm just going to deal with this here so I can kind of fix it. B goes to infinity, negative natural log. Square root of b squared is just b. So you get b times the square root of 1 over b squared plus 1 minus 1 over b. I guess I should have factored out a b from here too. So I can write this as b times all that. Okay, so now what happens? These b's cancel. The rest of the b's go to infinity, so 1 over b squared goes to 0. 1 over b goes to 0. You get the natural log of 1 over 1, which is natural log of 1, which is 1. So you get negative natural log of 1, boom, 0, plus the natural log of the square root of 2 minus 1. Which I have, I failed to factor on x from the square root. That's kind of what I did. I guess I could have done that up here. That's kind of what I did down here. I factored out the b squared, and it came out as a b. I'm concerned for one small reason, though. My answer is negative. And I'm pretty sure this has a positive amount of area. It's always disappointing when your answer doesn't quite work out the way you think it was supposed to be. Because it means I probably made a small mistake somewhere. Let's double check our integral real quick. Oh, I did make a small mistake somewhere. Very small mistake. I forgot the plus sign here. So I know I was seeing that it was negative because root 2 minus 1 is less than 1. It's like 0.4, and the natural log of a number less than 1 is negative. So that's an easy fix though, right? We're happy about this. That's a plus, 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 plus. Cool. So it did work out. Oh, sorry, there was some way to join. I kind of missed them, and I feel like it happened a while ago. Sorry, Jacqueline, if you've been waiting a while. I feel like I heard you beep in, and then I kind of got too involved in the problem I was doing. Okay. So I think we've talked enough about comparison, direct comparison. It's enough for the time we have. Let's switch gears and talk about the trapezoid and Simpson's method. Okay. So typically, a lot of the times teachers will give you these formulas on the exam. Where's the thing I was looking for? Yeah. Where'd you go, improper? Oh, sorry, not proper. Okay. So the idea here, the idea with these formulas is that we can use them to approximate the value of a definite integral that cannot be integrated. For example, both of this, the integral from 0 to e to the x squared, the integral from 2 to 8 of 1 over natural log of x, the integral from 0 to pi of sine of x squared dx. All of these integrands, e to the x squared, 1 over natural log of x, and then sine of x squared, cannot be antidifferentiated. There is no function that is the antiderivative of sine of x squared. Or, in other words, there's no function whose derivative is equal to sine of x squared, or 1 over natural log of x, or e to the x squared. I guess that's not entirely true. It's just that the answer is really dumb. Here's the function. Here's the function whose derivative is sine of x squared. There's a function whose derivative is sine of x squared. Right? It's kind of pedantic. There's no nice, there's a word I always struggle to find when I'm talking about this. There's no nice elementary function, which is just like regular functions added, subtracted together, whose derivative is this, or this, or this, or a whole host of other things. But we have numerical methods that allow us to approximate the area under a curve. So let's look at an example we actually do know the area of. Let's approximate, well, first, we'll approximate the integral from 1 to 3 of 1 over x dx. Now, we know the actual answer here. The actual answer would be, well, if I integrate this, I get the natural log of the opposite value of x from 1 to 3, which is just the natural log of 3 minus the natural log of 1. That's a 0. So you get the natural log of 3, which is approximately 1.0986. Yeah, I totally know off the top of my head. I was looking at my notes. So the idea with the trapezoid method, and I'm going to go to the other side because I want to draw a picture for you guys. The idea with the trapezoid method here is that we're going to use trapezoids, right? It's called trapezoid method for a reason. So I'm integrating this function 1 over x from 1 to 3. And I'm going to use, sorry, I lost my spot here. Yeah, let's use use n equal to 4 trapezoids to approximate the area. So I'm just going to draw some trapezoids. So first of all, I have to take my interval from 1 to 3 and break it up into 4 equal subintervals. So the length of my subinterval is going to be the total length divided by the number of subintervals. So 3 minus 1 over 4, which reduces to 1/2. So each of my subintervals where I'm going to have a trapezoid has a length of 1/2. So I'm going to have a break here and here. So I've got these 4 subintervals with endpoints that are 1 and 3/2 and 2 and 2.5, which is 5/2 and 3. And for each of these, we're drawing a trapezoid. So we're just connecting these endpoints. And in this case, since the function is decreasing like this, the trapezoids are going to be an overestimate. It's hard to draw them so they look kind of like above. I suppose I can make it a little more extreme looking. So if you want to kind of blow up this picture for just 1 second, you can think of it looking like, is that what you really wanted, James? I don't know. You can think of it as being like, sure, like that, where if I'm starting like, if here's 1, here's 3. Right. Here's maybe a little bit better way to see, like, oh yeah, here's my trapezoid, which is clearly above. And here's my trapezoid, which is definitely above. And so on. Where the area under the curve, right, is a little bit less, right? There's a small sliver that I'm missing, or that I'm overestimating by in this particular problem. So where is this trapezoid formula come from? Like, you might have seen something like 1 b minus a over 2 n times f of some stuff. Well, the idea is you're actually using the formula for the area of a trapezoid. So if I think of, this is my trapezoid for a second. I'm going to lay it on its side. So here's my trapezoid chilling on its side. It's having a rest. So it's a lazy trapezoid. And I'm going to call this here, we typically call the height. And this is the base 1, and this is the base 2. And the area of a trapezoid is exactly going to be the height times the average of the bases. And if you think about it, you can totally take the short base, the long base, the average is halfway between. If you cut this thing right here, you can cut this part off and put it back up over here. So, oh yeah, you just get a rectangle whose height is h and whose base is the average of those two bases. Great. So let's see what plays out here. So we have to be a little bit careful because in this picture, the height is really the base in this picture. And the bases are the heights. So when I find the area of my trapezoids in this picture, it's going to be the average of the heights times the base. So let's find the area. The area is going to be, I want to write this in a particular way, yeah. So let's write all the trapezoids. So it's going to be the first trapezoid is going to be, sure, the height, which is the base, which is going to be a 1/2 times the average of the height. So that's going to be this height here plus this height here. So that's going to be f of 1 plus f of 3/2 over 2. Okay, that's my first trapezoid. Okay, my second trapezoid, the height again is 1/2, or the base, right? And the average of the heights is going to be f of 3 halves plus f of 2. I'm going to run out of room. So there's my second trapezoid. And let's take it right up here. Sorry, I know there's limited space. Let's do this over here. Plus, we'll go up. Plus, the third trapezoid is going to be this trapezoid here. It's going to be 1/2 again times the average of the heights. So 1/2 times f of 2 plus f of 5 over 2 over 2. And finally, the last trapezoid is going to be, again, base times the average of the heights, f of 5 halves plus f of 3 all over 2. Okay, so there's another way we can write this, which is going to be much, much nicer. And I think it's time to erase this. Yeah. So look at how this plays out. So first of all, what can I factor out from both of these? Well, I can factor out, from all of them. I can factor out a 1/2 from all of them. And I can also factor out another 1/2 from all of them. So look at what I'm left with. So all of this is it's an approximation, so I should really be using approximation. And here is approximately 1/2 times 1/2 times, let's see what I'm left with. F of 1 plus f of 3 halves plus f of 3 halves plus f of 2 plus f of 2 plus f of 5 halves plus f of 5 halves plus f of 3. Or in other words, I've got 2 of everything except for the first thing, f of 1, and the last thing, f of 3. So this is going to be 1/2 times 1/2 times f of 1 plus 2 times f of 3 halves plus 2 times f of 2 plus 2 times f of 5 halves plus 1 times f of 3. Hopefully this formula looks a little bit familiar. This is, if you want to think about it this way, it's 1/2 times your delta x, where delta x is the length of the subinterval, or if you prefer, this whole front part here is your b minus a over 2n. Right, again, a is 1, b is 3, and n is 4. I feel like I'm making a dumb mistake here. Why am I saying b minus a over 2n? I don't know. Let me double check before I get too carried away. Yeah, why am I? There's something weird that I'm saying that is not correct. One sec. Well, let me just think about it here. Yeah, well, that should be right. You should be getting delta x is b minus a over n, the length of your subinterval, and then I've got a 1/2 because of all these 1/2s I'm finding out. So yeah, that's right. I'm just getting carried away. So okay, yeah, I don't know why my brain is like having a hard time thinking about this for a second. It's totally correct. B minus a over 2n is 3 minus 1 over 2 times 4, which is 2 over 8, which is 1/4, which is exactly what this is equal to. Great. And so then you can actually plug it into the function, right? So remember, our function was 1 over x. So if we actually plug this in, we end up getting 1/4 times 1 plus 2 times 1 over 3 halves, which is 2/3, plus 2 times 1 over 2, plus 2 times 1 over 5 halves, which is 2/5, plus 1 times 1/3. Again, apologies, things are a little messy here. You can calculate this. I don't really want to calculate it. I'm just going to tell you that it's approximately 1.1167. Not a bad estimate using only 4 rectangular trapezoids for natural log of 3, which is about 1.0986. And it agrees with our picture in that it is an overestimate, right? We saw, I know I erased my pictures, but we saw that our trapezoids were capturing a little bit more area than was actually into the curve. So our estimate should be a slight overestimate. A couple notes here. The error in our approximation. So the error approximately in our approximation is the difference in the actual value minus the difference between the actual and the approximate value. So it's the absolute value of the exact value minus the approximate value, which in this case is approximately 1.00986 minus 1.1167, which is equal to about 0.0181. So our estimate's pretty good, to within like 200ths. The reason I bring up the error is because there is a formula to approximate the error as well. And we should talk about that while we have a chance here. So, right, so the point is, sure, for this problem, we were able to calculate the integral to actually find the area, to know how good our approximation was. But what if we weren't able to do that? How would we know how good our approximation was? Well, there is a formula for the error. The error for the trapezoidal formula in absolute value is always less than or equal to b minus a cubed over 12n squared times the, what is that thing? It's the max of the second derivative. Where x is between a and b. So the error is always bounded by this for the trapezoid method. In this particular example, with a equal to 1, b equal to 3, n equal to 4, and our function equal to 1 over x. So we have to figure out how to maximize the second derivative. Yeah, go away, Adobe. Sorry. I don't know why it's popping. Oh my goodness, God. Stop. My computer is wanting me to do things. I'm like, no, don't. So, how do I maximize this? Well, I take the derivative. Sorry, I'm not maximizing this, I'm maximizing the second derivative. So this is x to the negative 1. The first derivative is negative x to the negative 2. The second derivative is 2x to the negative 3rd. Okay, there's a couple ways we can go from this point. One way is to actually take the next derivative and find the critical values and maximize the thing. But really, 2 over x to the 3rd on the interval from 1 to 3 is definitely a decreasing function, right? As x gets bigger and bigger and bigger on this interval, 2 over x to the 3rd gets smaller and smaller and smaller. So this is definitely going to be maximized. So the maximum of f double prime of x on the interval from 1 to 3 is going to be at 1. Right? F double prime of 1 is going to be 2 over 1, which is 2. F double prime of anything else is going to be smaller than that on this interval. So our error for the trapezoid method is going to be less than or equal to 2 cubed over 12 times 4 squared times 2. Which, let's see, 8 times 2 is 16, 4 squared is 16, those cancel, you get 1 over 12, which is 0.0833. So for this estimate with this many n equals 4 trapezoids, this is the most the error could have been. We certainly agree with that because we actually found the error to be much smaller. Okay. Let's do an example. Oh, where'd you go? Example that I had. So, I don't know where I put it. Someone wrote me a method. Yeah, okay. Someone asked this question, which I thought was worthwhile. Might have been over question, that's fine. So the question here is, how big or how many subintervals do we need to use so that the error in estimating the integral from 1 to 2 of 1 over x squared is less than, it goes 10 to the negative fourth. Now, of course, this is kind of a silly question because we could just integrate that, right? But we'll still play along. So notice they're not actually asking us to estimate the area under the curve using any number of subintervals. They're just asking us to tell me how many subintervals would you have to use if I wanted my error to be less than 10 to the negative fourth. Well, so using the trapezoid method, right? Because it's a different question if you're using Simpson method, which we'll talk about next. So here's my error formula. The error, if I'm using the trapezoid method, is less than or equal to b minus a to the, what is it, third? Yeah, third. Over 12n squared times the maximum of f double prime. Some books call this thing k, and they're like, k is the maximum of f double prime of x on the interval. And we want this to be, so we want the error, which is less than this, to be less than 10 to the negative fourth. All right, so we have to plug in for everything. So b minus a is 1. N is what we're trying to find. And the max here we have to figure out. So let's do it on the other side. So f of x is 1 over x squared, which is x to the negative second. I thought f prime is negative 2x to the negative third. F double prime is 6x to the negative fourth, which is 6 over x to the fourth. And we're once again lucky in that the second derivative here is a function that, at least on the interval, is always either increasing or decreasing. Right, so if we're on the interval from 1 to 2, you can even graph this if you wanted. Right? F double prime of 1 is 6 over 1. F double prime of 2 is 6 over 2 to the fourth, which is 6 over 16, which is like 3/8. Now, well, actually, I have a pretty good idea what this looks like. It looks a lot like this. So on the interval from 1 to 2, it's really, really clear that 1 is where you're going to get the maximum value. So this has a maximum value of f double prime of 1, which is equal to 6 on the interval from 1 to 2. All right, so let's go back and plug everything in. So let's see. We need this to be less than that. B minus a is 1. 1 cubed is 1. So 1 over 12 n squared times 6 is less than or equal to, I prefer to write this as 1 over 10 to the fourth, or 1 over 10,000. I'm trying to solve for n. I'm going to cross multiply. And I might even cancel a 6 there and a 6 there. So I'm going to multiply the n squared up over here and the 10,000 over there. So we get 10,000 over 2 is less than or equal to n squared. So n squared is bigger than, or I should say 5,000 is less than or equal to n squared. So n is bigger than or equal to the square root of 5,000, which is equal to, what's the square root of 5,000? Good question. I think it's like 70, I want to say it's 70 point something. Okay, come on. Ah. Why is my calculator just not wanting to do anything? Wow, what is going on here? Okay, I did something bizarre. Okay, anyway, square root of 5,000. And my calculator is going to tell me it's the square root of 5,000, which is really helpful. Oh, it didn't actually. Funny, sometimes it's just like, it's the square root of 5,000. It's about 70.7. So what do we pick for n? Well, I can't pick 70.7 subintervals. How many subintervals do I actually have to pick? 71. If you only pick 70, you might not be close enough. Your error might just be a little bit too big. So you always have to go up to the next one, even if it had been like 70 point, right, if I had gotten n bigger than or equal to like 70.0035, I'd still have to round up to 71 because you have to make sure you have enough subintervals. And this says n has to be bigger than or equal to 70.0035. 70 isn't bigger than that. So you can't pick 70. You have to pick the next biggest one, which is 71. Just be careful about that. When you're talking about how many subintervals you need for your error to be less than the number, you always round up to the next whole as integer. Or I guess next whole as integer, the next whole integer. I suppose you could also say you're using the least integer greater than or equal to your number function to get there. But that seems like a lot of words for not what we need. Okay, let's look at Simpson's rule, Simpson's method, Simpson's rule, which is another method that allows us to approximate the area under intervals. It's kind of cool. So the trapezoid method obviously uses trapezoids to estimate the area between each subinterval. Simpson's rule actually uses parabolas to estimate the area under each two subintervals. So for example, I'm going to draw kind of a wonky picture here. If I was trying to estimate the area under some curve from, let's say, here to here, let's say 1 to, I don't know, 9. Let's say I was going to be super lazy. I broke it up into let's break it up into 4 subintervals. So they're each too long, 3, 5, 7, right? And what Simpson's method does is they essentially say, okay, from here to here, there's one and only one parabola that goes through those 3 points. And I don't know exactly what it looks like. Maybe it's always hard to like actually pretend like I'm drawing this for real. Yeah. Maybe it looks kind of like, it probably doesn't look exactly like that. But you can but believe me when I say there is one parabola. So we would use exactly the area under this parabola, which wouldn't be perfect, but it would be close. And then from here to here, which is going to hit these 3 points, there'd be some other parabola. Maybe it looks like that. And we're finding the area under that. So that's the idea behind Simpson's rule, is that the rule actually, and we're not going to like derive it, but the rule actually does tell you the area under a parabola that goes through those 3 points. Or I should say, Simpson's rule is using a parabola through 3 points to estimate the area. So what's kind of neat about this is that if your function actually was a quadratic, Simpson's rule will estimate it perfectly. So let's say, yeah, that feels kind of silly though. We don't really need to do that. So here's how I remember the rules. The trapezoid rule so if I'm trying to estimate the area under a curve using n trapezoids, it's b minus a over 2n, or if you prefer, delta x over 2 times 1 times f of x of 1 or 0 plus 2 times f of the next one plus 2 times f of the next one, all the way to 2 times f of the second to last one plus 1 times f of the last one. Where your x of 0, x of 1, all the way to x of n are the endpoints of your subintervals, right? So we're breaking our interval from a to b up into n subintervals, where a is x of 0 and b is x of n. And this is like x of 1, x of 2, x of 3, all the way to x sub n. So that's how the trapezoid rule plays out, right? And we really just, right? And we talked about this before, how, right, it was one of the first thing, and then two of the next one, two of the next one, and so on. Simpson's rule is a little bit stranger. The way Simpson's rule works is it's going to be b minus a over 3n, or if you prefer, 1/3 delta x. And then the pattern isn't 1, 2, 2, 2, 2, 2, 2, 1. It's 1, 4, 2, 4, 2, 4, 2, 4, 1. So it's going to be 1 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3. Sorry. Yeah. And then all the way to, it has to end with a 2, 4, 1. So it's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So there's symmetry. The 1s are always next to the 4s. So the last couple terms will be 2 times f of x sub n minus 1 plus 4 times f of x sub n plus 1 times f. I blew it. Knew I was going to do it. It's 2 times f of x sub n minus 2, 4 times f of x sub n minus 1, and the last one is 1 times f of x sub n. Sorry, I know I got there. So, for example, how would I estimate the same thing? How would I do the area under 1 over x from 1 to 3 using Simpson's rule with n equal to 4? Okay, well, this one's real kind of short. I still like to draw the picture of at least the x, right? You can draw the function too. I really just want this. I'm dividing this up into 4 equal sections. They're still each 1/2 long. 3 halves, 2, 5 halves. And so the way it's going to work is, right, for these first 3 points, I'm going to have a parabola through them. And then for these second 3 points, I'm going to have a parabola through them. I don't really need to know that, but it's kind of nice to have some idea of what's happening. So here's what I get. I get the Simpson's rule approximation using n equals 4 subintervals. So here's my x sub 0, here's my x sub 1, x sub 2, x sub 3, x sub 4. And we do use all the points. So it's going to be 1/3 of my delta x, which is 1/2. I mean, delta x is just the subinterval length, times 1 times f of 1 plus 4 times f of 3 halves plus 2 times f of 2 plus 4 times f of 5 halves, and then at the last one, so it's a 1 times f of 3. So we end up getting 1/6 times, let's see, our function is 1 over x, so I get 1 plus 4 times 2/3 plus 2 times 1/2 plus 4 times 2/5 plus 1/3. You'll notice it actually has some of the same numbers, a lot of the same numbers as the trapezoid rule. It's just that some of the 2's are actually 4's instead of 2's. This ends up being approximately, what have I got here? 1.1000. Which is very, very close to what we're actually looking for. And then, yeah, we should also talk about the error formula for the Simpson's rule. So the error for Simpson's rule, let's do it here. So the error formula for the trapezoid rule, I'll remind you guys, is b minus a cubed over 12n squared times the max of f double prime of x on the interval that we're working on. The error formula for Simpson's rule is b minus a to the fifth over 180n to the fourth times the max of f, the fourth derivative of x. Wow. Okay. So in this problem, it's still not terrible. We can find our function is 1 over x. Our first derivative is negative x to the negative second. Our second derivative is 2x to the negative third. Our third derivative is negative 6x to the negative fourth. And our fourth derivative is 24x to the negative fifth. Whew, it's a lot. I feel like I made a mistake. No, I don't make that. Okay. So on the interval from 1 to 3, the fourth derivative being 24 over x to the fifth, it's going to be maximal when x equals 1. And a lot of these problems are designed in such a way so that you don't have to think too hard about where this is going to be the most. Right? This is definitely going to be the most when x is as small as possible. So maximum is 24. And so then, yeah, okay, fine. So then my error for the Simpsons method is going to be b minus a, which was 3 minus 1 to the fifth over 180 times n to the fourth, n was 4, times the max of this, which is 24. If we solve this, we get something heinous. We get, where'd you go? Sorry. We get a number that's not very nice. We get 0.0167, which looks to me like 1/60th is what that is. That seems wrong. Anyway, that seems right. Because 1/6 is 0.167, so 1/60th would be 0.0167. Okay. Our error was definitely less than that. Great. Let's see. There was one other thing I wanted to say. Okay, yeah. Here's the last thing about this particular example, and then we'll move on to one other example. I know there's a lot of number stuff. So just remember, I know just the formulas. The formula for calculating the approximation for trapezoid and Simpsons is either one of those two formulas, where it's the 1 2 2 2 2 2 1 formula, or the 1 4 2 4 2 4 2 4 1 formula. And then the error formulas are these formulas here. So they can either ask you to approximate the thing, or they can ask you kind of like, how big should m be so that our approximate is as accurate as possible. So let's look at these two, maybe three examples. What n do we need so that the Simpsons rule estimate is accurate to within, what have I got here? 10 to the negative fourth again, for the integral we were just talking about, integral 1 over x dx from 1 to 3. This is where we're going to get an interesting answer. So the error, we know, is less than or equal to, formula is always like, what's this formula again? Oh yeah, it's b minus a to the fifth over 180 n to the fourth times the maximum of that on the interval, which we just saw was 24. We want that to be less than or equal to 10 to the negative fourth. Okay, let's simplify this a little bit. This is, let's see, 2 to the fifth is 32 times 24 over 180 times n to the fourth, less than or equal to 1 over 10,000. I'm pretty sure I can cancel some things, like, let's see, 24 and 180 both have a factor of 3. 8, that's 60. And then 60 and 32 both have a factor of 4. I guess it's 8, right? If I cancel 4, cancel 4. So here's what I've got. I'm going to multiply the n to the fourth up here and the 10,000 up here. So I'm going to have n to the fourth over here. And over here I have 32 times 2, which is 64. over 15 times 10,000. So 64 times 10,000 would be 640,000. All right. What do we get here? So let's take a look. So that means n is going to be bigger than or equal to the fourth root of this gross number, 640,000 divided by 15. Let's see what we get. 640,000 divided by 15 is 42,666 approximately. And then the fourth root of that, so to the 0.25 power, is about 14.37. All right, so let me ask you guys, what does my n have to be so that it's big enough? I was hoping I could trick you guys, but you're too smart. Yeah, Morgan, you are exactly correct. N has to be 16. Because although I didn't say it, clearly someone has said it, or you already knew that for Simpson's method, the number of intervals has to be even. If you don't have an even number, then you don't get the 1, 4, 2, 4, 2, 4, 2, 4, 1 pattern happening. You end on the wrong iteration of it. And also, if you think about the picture I was drawing, right? If you think about it, the reason you need an even number of intervals, right? So let's say we have x0, x1, x2, x3, x4. Each set of 3 has to give you, or really I should say, each 2 intervals is where you're going to be using a parabola to estimate it. So, right, for this first 2 intervals, there are 1, 2, 3 points. And those points, you draw the parabola through them. And then for this next 2 intervals, use the 1, 2, 3 points. So maybe it's, I don't know, something dumb like this, right? But the whole idea is you have to have an even number of intervals because you're breaking it up into a bunch of sets of 2 subsequent intervals. So you have to have an even number. So yeah, you do round up to the next biggest even number, which is 16 in this case. Okay, cool. Sorry, excuse me. I got time for one more, maybe. Yeah, I do want to throw this one at you guys. So let me show you this. Because so far all of our maximal part has been pretty easy. Here's one that's less easy. Let's say I wanted to estimate the integral from 2 to 8 of 1 over the natural log of x dx using the trapezoid rule with, I want to find n so that the trapezoid rule is accurate to within, what do we got here? 10 to the negative third. All right, so trapezoid rule, it's going to be now b minus a, right, b minus a cubed. Yeah, b minus a. Did I do the last one right? Yeah, I did. B minus a cubed over 12n squared times the max of the second derivative less than or equal to 10 to the negative third. I need to know what that is before I can go on. So let's actually figure that out. Let's figure out the max of f double prime on the interval from 2 to 8. And this part's going to be a little bit trickier. So the max of f double prime, so f of x is 1 over the natural log of x, or the natural log of x to the negative 1. The first derivative is negative natural log of x to the negative 2. And the second derivative is, times 1 over x. And my second derivative here is going to be kind of gross. Let's see, so I use the product rule, it's going to be 2 times the natural log of x to the negative third times 1 over x. Plus the negative natural log of x to the negative second times the derivative of this, which is negative 1 over x squared. Yeah, that's looking pretty gross. If I multiply, let's rewrite this. This is 2 over x times the natural log of x cubed plus, plus 1 over x squared natural log of x. squared. So I get a common denominator by multiplying this by x over x, and this by natural log of x over natural log of x. So here's what I've got. I've got 2x plus natural log of x over x squared times the natural log of x cubed. And again, I'm on the interval from 2 to infinity. 2 to infinity. Not infinity, upright infinity. Okay, I know it's 302, so I should cut it short here. The idea with this is I'm not going to take the derivative of this and set it equal to 0 to find any critical values. That's terrible. What I'm going to do is I'm going to say, well, I just want to make this as big as possible, even if it's really bigger than it can actually be. So to make a fraction as big as possible, I'm going to make the top big and the bottom small. So I'm going to let the top have 8 for all the x's. So this is definitely going to be no bigger than 2 times 8 plus natural log of 8. I feel like I'm making a small error here. I'm just looking at my notes. Oh, I did make a small error here. It's a small one, but I just want to point out, I forgot that when I took the derivative of this to multiply by another 1 over x. Right? I did my chain rule for this, but then it's also multiplied by 1 over x. So I actually didn't need this x here. Sorry about that. So I'm going to let the top have an x value of 8 to make it as big as possible. So I got 2 plus natural log of 8. And at the bottom have an x value of 2 to make it as small as possible. So I have 2 squared times natural log of 2 cubed. And that, if you use a calculator, is approximately 3.06. So that's our upper bound for the max. Now, is it really going to be that big? No, but it's okay. You can use a number that's too big. So then this would be 8 minus 2, which is 6 cubed over 12 and squared times 3.06, less than or equal to 1 over 1,000. And then we'd solve for n by cross multiplying. So I'd have 1,000 times 6 cubed over, over 12 times 3.06 less than or equal to n squared. This number here is about 55,080. So n is going to be bigger than or equal to the square root of that, which is about 235.7. So 236. So the point I'm trying to make here, which I maybe did not the best job of, but the point is that you don't have to be super precise for all of these. You can kind of say, I'm going to make the top as big as possible and the bottom as small as possible, and that'll be a perfectly fine upper bound for the maximum of my second derivative here. All right, I should stop talking.